be able to see something here. Welcome to another computer musing. This is 11 years in a row now that I've been given a lecture about this time of the year, where I'm trying to tell you what I think the coolest thing I learned about trees was during the year. And I guess my main announcement for today is that this year I finally got I finally finished writing a lot of the stuff up about trees that I've been talking about in past years. If you can put this on the screen, this is now. If you go to my home page and ask for wow, okay, I got a funny monitor here. If you go to my home page and then go to the news page, and it'll tell you how to click and get this this preprint, and it includes a lot of stuff that I was talking about. Like last year, I talked about how to find all spanning trees of a graph, and so that's in here somewhere. Where are we talking spanning trees? Here, here we're doing spanning trees. Okay. Go back a little bit. We got something called the Christmas tree pattern. This is what I talked about 2 years ago, I think. When the title was called Chains of Subsets, but we decided to call it the Christmas tree pattern. There's lots of cool stuff I haven't talked about in class about that. If you take random trees and then you plot where the nodes lie, you get this kind of a pattern. Many other beautiful stuff about trees. I talked about lattices of trees a few years ago. I think Lau remembers that one. So those are here, pictures of different lattices of trees, and so on. So I'm happy that at last all this stuff I've been thinking about for years and years I got down in paper, and it seems to be it seems to check out and work. And today I'm talking about sand piles and spanning trees, which is something I learned about just before I finished writing this section. In fact, it's exercise 103 in these notes. In fact, I thought I would find it by looking in the index just before the lecture today, and I see that I've omitted the word sand pile from the index. Unfortunately, so I have to pay myself $2.56. But if you find any other errors in this version, then you can get $2.56 for it. So sand pile should have said right there on page 42. But here we are, exercise about sand piles, and then the answer coming up. So this is one of the most fantastic things. Like it's almost unbelievable, but it started about 15 years ago by a physicist named Dar. And let's see, I'm just training the camera operator here. Can you zoom up? Here you see. Here's how he writes his name in Hindi. So he started this all, and there's been lots of papers in the physics literature about sand pile models. But the curious thing is that it works also for people like me who want to deal with discrete stuff, and as we'll see that there's a huge number of results about graphs and trees that relate to this physics model of sand piles. Now, on page 70 is the reference then to the physics literature and so on. Now, in the Christmas spirit, I've decided that whoever asks the best question today, since you haven't been responding very much to what I'm saying here, so I got to see if anybody's paying attention. But whoever asks the best question, I'll give you a present. And you can either have, these notes, which of course are free on the web, or you can have a copy of The Art of Computer Programming, Volume 1, 2, or 3, or you can have the tech book here, or you could, and whoever asks the best question and reads Japanese can have the Art of Computer Programming Volume 1 in Japanese, because they sent me 4 copies and I only needed two of them, or actually only needed one. So I kept one for next year's Christmas present. All right, so there you are. I got 1, 2, 3, 4, 5, 6 presents here. That you can choose if you ask a decent question. Now, yes, Dan. What is the question that will give you a gift? Okay, so we put you in the queue right there. All right, now, so Dan is so far ahead of everybody in these things, and if he reads Japanese, he has a choice of 7 gifts. Okay, but what is this all about sand piles? Well, it actually this model applies to an arbitrary directed graph, almost arbitrary directed graph, which I think everybody knows what a directed graph is. The only condition that I'm putting on a directed graph is that there's a designated vertex in the graph, which we call vertex 0, and there's a path from everybody to vertex 0. So the graph is not only connected, it has this, it's called a sync vertex. So this means that, in particular, there's a way to make a tree, an oriented spanning tree on the graph. This means for every vertex except x0, or v0, I guess we call it, we give one arc coming out of it that gets it closer to v0, and then by following these arcs, we'll eventually get to that root. So there's at least one oriented spanning tree in the graph with the root of v0. And that's the only condition that I put on a directed graph. So of course there's a zillion wonderful directed graphs that each have different meanings to us, and for each one we can play the sand pile game. Now I'm going to illustrate the sand pile game on just a very simple case, which is actually a graph, not a directed graph. I'm going to consider a 3x3 torus, just because it's about the right size for the examples that I want to do. And it means that there are 9 vertices, and we'll call them 0, 1, 2, 3, 4, 5, 6, 7, 8. That's where I stop, at 8. And then each one is adjacent to the ones next to it, horizontally and vertically, and also it wraps around. That's why I call it a torus. So this one goes and wraps around and comes up. You can think of 6 as being up here, 6, 7, 8 as being up here, sort of a shadow effect there, and similarly 0, 3, and 6 are over at the right, and 0, 1, and 2 at the bottom, and so on. So this is a graph which every vertex has 4 neighbors, and it's a directed graph in the sense that each of these lines means there's an arc going to the right and an arc going to the left. Okay, now we play the following game on the directed graph. We put pieces of sand on every vertex except the special vertex v0. You put sand on there, and just for the heck of it, let me imagine that I put 4 grains of sand on each one. It can be any number, any non-negative number. But if it was all 0, we wouldn't have any fun, because I'll tell you what the rules of the game are. The rules of the game are, if any vertex, well, I'll specialize for this particular graph, and you'll see how it works for any directed graph. So in this particular graph, if you have at least 4 grains of sand on a vertex, then you can take 4 away and distribute 1 to each neighbor. So for example, this one has 4, so I change it to 0, and I put 1 on each of its neighbors. That's 1 goes here. I didn't list the number of the sand on this guy. So 1 goes here. This guy now has 5. 1 goes down, and so this guy has 5. And 1 goes up, so this guy has 5. And 1 goes to the left, but that's vertex v0, so it disappears. So we lost the grain of sand there. But otherwise, you know, okay. Now we repeat this process until we can't do it anymore. So as long as somebody has at least 4 grains of sand, then we can, you know, then we do this operation. It's called toppling. Toppling at a vertex, and a sequence of topplings is called an avalanche. So this is what this, you know, comes from physics. You have a question? Can you travel to a vertex? Can I what?
Travel to a vertex with no sand on it.
Yeah, you add 1 to each of the neighbors. But this guy, I didn't write anything there because he's a hole. The sand goes down into the, you know, into the inner earth and the middle earth and disappears there. Yeah, but now you're ahead of Dan in the question in the question competition. Okay, but now what do you think? Okay, now I'm just going to cycle through here and I'm going to take the first guy. I'm sorry, going to go to 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, and keep doing this until I've gone through several, you know, 8 steps in a row without making a change, and then I'll be stuck. So 5 comes up next. So what do you think is going to be, you know, test if anybody knows the rules of this game. What's going to be the situation afterwards? How many is going to be on, you know, in place of this 0 here? Yeah, you got it? 1. How much here? 1. Yeah, it was 1 left. We take 4 away. 1 goes to the left, 1 goes up, 1 goes down, 1 goes to the right and disappears. And so this is going to be 4, 5, 5. And this will be 4, 5, 5. Okay? Now, once more to warm you up, and then I'll show you the whole. Then I'll start doing it myself. Okay. So this 4 again, we're going to lose 1. It's going to go up, left, right, and down. So north, south, east, west. So this goes 0. We're going to have 6. We're going to have 6 coming over here. 5, 5, 5. All right. And okay. Now I'm at this place. The 6 is going to move, and it's going to leave 2 there in the middle. And okay. So I get 2, 1, 1, 2, 7, 5, 6, 5. And you can trust me on this. I had a computer program do this morning so that I wouldn't screw up. So the next step, we're changing the 7, and that gives us 2, 2, 2, 3, 3, 5, 6, 6. Then we go 2, 2, 3, 3, 3, 1, 7, 7 as the 5 topples. This first 7 is going to topple here. That's giving us a 3, 2, 3, 4, 3, 2, 3, 8. 8 is toppling, and we're getting 3, 3, 3, 4, 4. This is getting nice and symmetrical, 3, 4, 4. Now, you know, this would make a wonderful Java applet to put on the web, where you could just watch this thing toppling away. Now, before I finish, you know, or maybe I'm going to get into a loop. What do you think? Is it possible that this could go on forever? What do you think? Yeah.
Well, not each time, but a lot of the times you're losing one into.
When I'm losing a grain of sand, I'm certainly not getting in the loop. So yeah, right. So if I'm losing a grain of sand, I'm certainly making some kind of progress toward a different state. But could I possibly then go for a cycle and never lose a grain of sand?
So one of your grains is always moving towards the hole because there's always a path to the hole?
That's true. One is always moving towards upwards. All right, and that's the secret. In general, I have a directed graph, and every vertex has a certain out degree, and that out degree is the number 4 in this example. All right, so if you have as many grains of sand as your out degree, then you send sand to every one of the people for who you have an arc out of you. That's the rule for the general directed graph. In the general directed graph, I assumed that there was a path to 0 from everybody. That means that I can arrange the vertices into an order so that everybody has an arc coming out that goes to a lower numbered vertex.
Are all the arcs here bidirectional?
These are bidirectionally in the torus, but in the general case, not every theorem I'm going to talk about today works for every directed graph. I'll tell you what the restrictions are. But most of the theorems work for every directed graph that has at least one oriented subtree with the root 0. So this is so the point is, though, that if everybody in the directed case is going to have at least one neighbor that's lower numbered, that means that if you don't lose any sand, then you're always increasing in lexicographic order. You're always increasing the state where we list the number of pieces of sand on each one, and so you can't increase and increase indefinitely, and so you can't have a cycle. So now I have a lot of visitors, probably some of you can speak Japanese. I have to tell you, the people who came in, there's a prize offered to the person who asked the best question, like why didn't you wait for me, and especially the one who asks the best question and reads Japanese can have the art of computer programming in Japanese. Okay. Now, so as I'm saying, eventually we're going to get to a stable state, and stable means that there aren't any topplings left anymore. That means that every vertex, in this case, has has 3 or less guys. Yeah. Then you can't topple.
Do you skip it?
Right now, I'm skipping it. Yeah. Now that's my next question. What happens if I took another algorithm for this instead of going through 1, 2, 3, 4, 5, 7, 8? What if I use some other, like I've got where's this 4, 1, 6? Now I had this 8 here. Maybe I should have. Maybe I could double topple from the 8 and send 2 guys out. I didn't do that. I only went to 4 here. Okay, but anyway, I got I'm still toppling away here, and for the people who just walked in, see if you can guess the rule that I'm using. But what I did is I took the 6 grains of sand here and I sent 1 up, 1 to the left, 1 down, and 1 to the right. But down means it came back in at the top, so this 4 went up to a 5, and going to the right changed this 4 to a 5. So now I got 5, 2, 2. 1, 6. 5, 3, 2. I'm toppling now this 5, the first 5 there. And now I topple this 6, and that gives me 2, 2, 5, 3, 3, 5, 3, 3. Now pretty soon we're going to see that we're actually in a well, I guess this is getting kind of boring now, so I'll show you, just see if you can read it off of my notes, the cheat sheet here. So we got here, and I finally got to this state. See this one, 3, 3, 3, 2, 2, 3, 2, 2. So on and on and on, it gets to 3, 3. Trust me, 3, 2, 2, 3, 2, 2, and the total number of steps was 1, 2, 3, 4, 5, 6, 7. 8, 9, 10, 11, 12, 13, 14, 15, 23, 24, 25, 26, 27. After 28 steps, here we are. Yep. That is an excellent question, and that is what I wanted somebody to ask. So you're way ahead now. So now that's the question. What if I did the topplings in a different order? Okay. And so the first theorem is, it doesn't matter. You always get the same final state no matter which way you did the toppling. Now, how do we prove that? And, in fact, there's lots of theorems in mathematics that are much harder to prove that use the same idea. Yeah, you got to...
I'm not sure of the theorem. We always get to the final state from the initial state. So if we had started with a different...
Right. So here's the idea. Imagine that this is a state.
The final state depends only on the initial state, not on the order.
Only on the initial state, not, yeah. So here's some state, and maybe there's 6 vertices that can topple. Okay. So I have 6 ways to go from here to other states, depending on which one I chose to do the toppling. Okay. And these again, each one might topple, might have different ways of toppling. And eventually, and at the end, we finally get stable states at the bottom where there's no more toppling possible. All right. Imagine this big network. We showed that there's no infinite branches here. Every branch eventually comes to a stable state. The theorem is that all these stable states are identical.
The question was, does it depend on the initial state?
It depends on the initial state for sure. Yeah, because if the initial state was 3, 3, 3, 2, 2, 3, 2, 2, that would be the final state. But if it was 3, 3, 3, 3, 3, 3, 3, 3, that would be the final state.
Yeah, but if it had been...
Yeah, so it certainly does depend on the initial state.
Even if it had been...
There are, how many stable states are there in this case? You know, you've got 4 choices in 8 ways, so that's 4 to the 8th is 2 to the 16th, so that's, 6, 5, 5, 3, 6 number of stable states that can occur. But so for each initial state, there will be one stable state afterwards, and I want to prove that. And so what the way you prove it is, suppose that you have 2 choices. I mean, you've got more than 2, but let's suppose you had 2 choices. So from one state you could go either topple at vertex 10 or topple at vertex 15. Okay. Well, all you have to realize is that if you can topple at both places, okay, then you could do 10 first. Then one of the options is to come back from 10 to 15, and one of the options from 15 is to come back from 15 to 10, and that gets you to the same to the same one. So in any case, it's called a diamond lemma in many arguments in mathematics. That if you want to show that, like one of the most famous things is the somebody Kleene theorem about lambda expressions. But there's many different things also in unification theory. So if you can go 2 ways, but then you come back to the other, then it turns out these are all going to be identical. And the proof is that well, you could have done it. If you could do first I then J, then then you can always assume that. If these operations are commutative, you can always assume that you do it in your favorite order. Okay, so it's true, and therefore, if X is a state, Lyle.
If it's possible to do I and then J, it may not be possible to do J first because J may not be toppleable unless it gets one from I.
That's okay. That's okay. If there's 2 ways out. If you have 2 choices as to what to do next, then you can do them in either order. And this is the same argument that you use when you're trying to prove the Knuth-Bendix theorem or something like this. It's all these arguments are the same. And in fact, if you still aren't convinced, use induction on the length of the number of topplings, and then you see that if something can go 2 ways, then this one has the same number of toppling. All outcomes of this one are equal to this. All outcomes of this one are equal to this also. Therefore, these are the same. Therefore, this is the same. So it's a theorem, and so if you have any state X, it goes to a unique state, which are called sigma of X, the stable state that happens if X is your initial configuration. Yep, I'm getting great questions here. I love this.
Is it true that the order of toppling can change the number of iterations before it reaches the final state?
Is it true that what?
But the toppling sequence, can change the number of iterations.
Actually, this proof that I just gave shows that it's actually also going to be the same number of iterations and the same number of topplings at every vertex. In fact, that's also going to be obvious from another thing that certain vectors are linearly independent. But okay.
I'm just thinking if you have zeros and a 4 and a 3.
Yeah.
Right. You'll go through one side. If you start with the 3, it'll do nothing. Then you do the 4.
Yeah, it's okay. Yeah, but you can't start with the 3 because the 3 won't topple.
Right. And then the next. Whereas if you did it the other way, you'd have the 4 would topple and then the 3 would.
There's only one candidate there.
There's only one candidate here. You have to start with the 4 in this case.
Yeah, the failure of toppling does not count as a move.
Failure of toppling does not count as a move. In that sense, some strategies could be very bad because they would always look at a vertex that you don't want to topple.
Is this a result only about toruses, or does this generalize?
It's true for every directed graph that has an oriented spanning tree. the root z1. This defines a mapping to stable states. Yep.
I'm presuming that in general, the rule of this game is that you can topple if the number of sand grains is at least the out degree of a vertex. You have an arbitrary.
Exactly. Yeah. You never run out of sand at any vertex.
And
so if a vertex has 5 arrows going out of it, to take your favorite directed graph, it's probably got this property that you can get from it. Okay. Then you can play the sand pile game on it. And you can keep on going, and you can write your Java applet, and you can keep on going until it all percolates, and at the end you got a stable state.
What's the complexity of computing sigma x given x?
It's unknown to me. In fact, there's going to be an almost uncountable number of open problems raised by this. It's a fantastic area to think about. Although I have to say I don't know of any practical applications at all. I mean, but so here I'm talking beauty here.
Given this torus, given a stable state, add 4 to every non-whole vertex.
Yeah. And
run your algorithm. Do you get back to that stable state?
No, because I would get. You see, that's not equivalent to 0. If I added the difference between 4 and 3, then it might happen. In fact, that's the next. You're very good. You're anticipating my next.
Yeah. If we go to 7,
okay,
7,
so
7.
So anyway, I now define what sigma of x is. Okay, x is a vector of called a state. It means how many grains of sand do I have. X in here is an A-tuple saying how many grains of sand are on each vertex, and we'll focus on this particular torus graph for now. So there is this function sigma of x that depends on x that I just told you about and exists. Okay, now let's try to figure out something about the states. Now we know how many stable states there are. It's obvious. You just take the product of the degrees, and 4 to the 8th in this case. But some of the state. But now the physicists are interested in what they call recurrent states, and this means that if we allow nature to introduce grains of sand at random from time to time, and then that causes toppling to occur, then some states will occur infinitely often. But a state like 0 will never occur again. Nothing ever leads to the 0 state. Okay, so the interesting ones are the recurrent states, the ones that you can get to again. So I wrote this computer program. Maybe I should put it on the web, but you can. Here's a program that I'll probably put it on the web tonight. Simple playing with sand piles on a 3x3 torus, and then I explored adding 1 grain at a time. Okay. And then I did some more experiments, so I said let's keep putting 1 grain of sand. Let's start with all zeros, and then we put and then I'll put 1 grain of sand on this vertex here, so I get 1 0 0 0 0, and then I put another on and another on and another on, and what happens? And it turned out that it starts to spread around. The sand goes around and around, and I get, eventually, it gets into a loop, of course, and it turned out to be a cycle of length 18. So you think, oh, this is probably a recurrent state, because it recurs if you keep on adding sand on that one vertex. I'm getting these 18 things. But still, there were a lot of states I hadn't hit yet. So I went to one of those, and I started, and again I kept adding sand until I got into a cycle. I got another cycle of length 18. I don't know if the cycles were all of length 18, but I kept doing this until I started with every possible state, and I had gone until I reached a cycle. This is called so. Anytime you have a mapping that goes from x to sigma of x, this is called a functional digraph. It's a mapping of the set into itself, and the only possible. And so you started at a vertex x0, and then you go to x1, x2, x3, and eventually, actually, I should draw it like this because it always looks like a 6. No matter where you start, there's a certain tail, and then eventually you get into a loop. You take any mapping of a finite set into itself. I said, okay, I wonder, what about all these, how about all of the vertices that are in these loops? 0, 0, 0 isn't in a loop, but eventually it did, and this was a cycle length 18. Well, there were 26,000 in some of these vertices. However, it turns out that the number of recurrent states in this torus is actually 11,000 and something. So that meant there were 15,000 in these loops, but they still aren't recurrent in the sense that they would keep occurring in nature if we kept adding on adding sand. This is only a small number of such. It's not really what a recurrent vertex is, and so the real definition of recurrent. And by the way, that's an error in the paper that introduced this subject in Combinatorica in 1999. The paper which inspired me to study it asserts that something is a recurrent state if it has the property that x is a recurrent state if x is equal to sigma of x plus a for some non-negative a. That was their definition. Some positive a. So a is a vector of It says you add sand to it and you get back to yourself again, and that was the definition of a recurrent state. But it turns out that that's not the right definition. Yeah.
Where you're adding grains of sand, and how. So you add one, and then you see if you can.
Okay, so what I did was I said I go from x. So let's say f of x is equal to sigma of x plus 1, 0, 0, 0. That's a function. So I map x into f of x. That was the experiment that I did. So I started with a state, and then I added one grain of sand, and I reduced it. I toppled, and then that was a recurrent state, and then I go from that to add another grain of sand over and over again. That's what I was finding these.
At the same vertex.
What?
You keep adding a grain of sand at the same vertex in this experiment.
At the same vertex, I was always adding it to vertex number 1, which was the first neighbor of
Have you thought about the inverse of the theta?
The inverse, there is no, we got to, a recurrent state will have an inverse, but a non-recurrent state won't, and that's important. So I got to get going. You guys are asking too many good questions, but a lot of the questions I can answer by getting on to my next thing, and that is to figure out what are the states that would occur infinitely often if we kept adding sand at random to all vertices, not just to the first vertex, and that's fewer than the states that would occur if we just add to a particular vertex. Okay, now, so the definition that I say is a recurrent state x, and that means that x is equal to sigma of y, where y1 y is is a state, which means there's y1 grains of sand on the first thing, and all of these numbers are 4 or more. In my example, or in other words, y sub j is greater than or equal to the degree of j, the out degree of j, at every point. This means, you see, that if we keep adding enough sand, eventually all of these components are going to get arbitrarily large, and so at some point they're at least going to get as big as the degree. And as soon as so for all of these, so let's just call it a kind of a heavy vertex or a large one. It means that every vertex has at least d sub j grains of sand on it, as much sand as it will topple at one. Then we look at all of the stable states that result from those inputs. Okay, not so certainly there's a finite number of stable states, and some of them will occur from big inputs, and some of them will never occur from big inputs. So the ones that occur from big inputs as stable states, those are the ones we call recurrent. No, it's sigma of y. If there exists a y for which sigma is x is sigma of y and y is equal to is a large state. Yeah, but your definition would probably no, I don't know. I think your definition would have to be true, but I'm not sure. It goes one way, but not maybe not the other. Yeah.
So the definition that I believe would be equivalent, you probably proved that it's equivalent, is that something is a stable state if for every state there's a state that's at least as big on all vertices that leads to X.
Yeah, I know what you're getting at, and that's also in my computer program. So for example, I tried now also looking at what happens if you add to vertex 2, and you look at the cycles that you get there, and 3 and 4 and up to 8, and so then I took the intersection. So something was in a cycle, a cycle by adding 1, a cycle by adding 2, a cycle by adding. Well, then I had 17,000 instead of 26,000. So I still had lots of things that weren't recurrent states. But the actual condition is this. In this 8 vertex graph, the actual condition is this. You can imagine the directed graph that has 8 colors of arcs. And put a red arc if it corresponds to adding sand on vertex 1, and put a blue arc if it corresponds to adding sand on vertex 2, and so you have 8 colors of arc. So then the condition is that you have to have one color of one arc coming into you of each color from a recurrent vertex, and you have to have at least one. No, I'm sorry. Everything coming out from you. The recurrent form a set that everything coming out stays in the set, and furthermore, everything coming in was in the set as well. You had one coming in of each color. It's a complicated thing, but it works. But there's a much better way to test for recurrent state. Yeah. So X is recurrent if and only if X equals sigma of X plus T, where T is D minus sigma of D. Okay, now D is the state where everybody has its degree. So D is the state that everybody has. I started out with all 4s. That was D. So example, D is equal to 4, 4, 4, 4, or in my case I wrote it 4, 4, 4, 4, 4, 4, 4, 4, 4 like this, and sigma of D was the final state that came out of it was 3, 3, 3, 2, 2, 3, 2, 2, and so T is the difference between these. Notice that sigma of D is always less than D, but every component of T is positive, strictly positive. And this is 1, 1, 1, 2, 2, 1, 2, 2. So in our particular case, D puts 4 everywhere, and that reduces, as we saw, to the stable pile sigma of D, and then we subtract that. We get something that has these components. Now I want to prove that. I want to prove this result. And if the proof goes too, it's not always nice to prove things in front of an audience and does anybody get it? But it is in this. It is in these notes, and I'm going to prove a few things, and I'm going to hand wave a few other things. but here's the thing. So I got to prove both ways. So if x is equal to sigma of x plus t, well, then it's certainly a stable state, because it's a stable state. It's sigma. Sigma is always something is a stable state. Then x is also equal to sigma of x plus kt for any multiple of t. I mean, I add t and I reduce, and then I add t again, and I keep reducing. Okay, so there we go. Now all components of t are positive, though, and so I can make k, big enough so that this is the vector y that I needed. Okay, so that's good. Now, conversely, if x equals d plus y, x equals sigma of y of, well, let me write it, it's sigma of d plus y, where all components of y are non-negative. Okay, so if x is sigma of d plus y, then it's a recurrent state. Then d plus y plus t topples to x plus t, because we know that d plus y topples to x, and I can leave these t sitting there. But it also topples to sigma of d plus y plus t, because I know d topples to sigma of d. But this is equal to d plus y. Okay? So, therefore, sigma of x plus t has to equal sigma of d plus y. Keep toppling these until they get to state. So these are equal, and that's what I wanted to prove, because this is x. I'm sorry, this is x. So sigma of x plus t is equal to x. So I now proved both ways of this thing. So this is a nice one-test characterization of a recurrent state. And now comes the mind-boggling theorem. It says that the number of recurrent states, anybody want to guess? Number of recurrent states is the number of oriented spanning trees rooted at V0. Let's just say number of spanning trees in the case of a graph an ordinary graph where we don't have a directed graph. But in general, it's the number of oriented spanning trees with root 0. Okay. Now that is the beautiful connection, because you see, mathematics goes ahead by showing that two things that that are defined in completely different ways actually are in some sense the same. That there's a correspondence between x and y, where x and y are defined completely different intuitions. And so now this is the first theorem that we that Dar actually observed, the physicist. And well, the proof is actually there's the proof that he gave was algebraic, and was just showed that there's the same number. And I'll show you how it works, but I won't go through the details except to wave my hands. But what we do is we look at the so-called Laplacian matrix of the graph, and let's take let me show what the Laplacian matrix looks like in the 3x3 torus. So the Laplacian matrix is a matrix where we have one row and column for every vertex of the graph, and then on the diagonal we put the degree, and it's 4. Everybody has degree 4 in this graph. 3, 4, 5, 6, 7, 8, and then we put minus if it's adjacent. So 0 is adjacent to 1, 2, 3, and 6. I could write -1, but I don't have room. And then 0 is everywhere else here. So vertex 1 was adjacent to 0 and 2 and to 4 and to 7. and this one was like this, 0, 0, minus 0, 0, 4, minus, minus. Here it looks like this in this torus. 0, minus 0. This will be 0, 0, minus 0, minus 0, 0. This is just there's a two-dimensional structure to this, a sign of a Kronecker product type of thing. A minus minus here, minus 0, 0, 0, minus. Okay, this is the Laplacian of that guy of the torus, and the well-known matrix tree theorem says that the determinant of the if you toss out row 0 and column 0 and take the determinant, you get the number of spanning trees. And similarly for oriented spanning trees, it also works for the number of oriented spanning trees of anything. Now that's a theorem that has lots and lots of practical applications. Now, but you see this, you can also think of these vectors of this matrix here as what happens under toppling. Because every time I'm toppling, I'm subtracting, like if I'm toppling at vertex 1, I'm subtracting this vector from the state. I'm subtracting 4 from 4 grains of sand here, and I'm adding 1 grain at 2, 4, and 7. All right. So in other words, toppling toppling at vertex I says that x is being replaced by x minus a sub I, where a sub I is the ith row here. And so what's happening is then that I'm looking for the number of vertices that I can get that have all their components less than 4, but toppling preserves it. So let me say that x is equivalent to y if x minus y is equal to some linear combination of the C1A1 plus CNA, and if x minus y is some linear combination of these rows, then we'll say that those states are equivalent. Yeah.
Does it have to be
a positive? No, not in this definition of equivalence.
Okay.
Okay. So now I'm still not done with the theorem, but I do know that the number of equivalence classes is the determinant of this thing. That's linear algebra. We can take this matrix, we can use row operations and triangularize it so that we have all the entries on the diagonal are integers, and then the determinant, and then we get the determinant. In fact, they stay positive. This is a diagonally dominant matrix. So we can prove that the determinant is the number of equivalence classes. What we want to show is that every equivalence class contains exactly one recurrent state, and then the number of recurrent states equals the number of equivalence classes. Okay, so then the next thing is every vertex is equivalent to is equivalent to a recurrent vertex, is equivalent to some recurrent vertex, recurrent state. All right. All right. Well, the idea is that because I can triangularize this matrix, it's going to turn out that x is equivalent to x plus n times b for some vector, because n is the determinant of the matrix. So the determinant of the matrix, I will be able to triangularize this thing, and then I can show that if n is the determinant, each one of the entries on the diagonal is a divisor of n, and so I can show that this is true for an arbitrary vertex v. For arbitrary v, I can add n. I can add n 0 to x and still equivalent. I can add 0n. All of these things are equivalent. So every class contains a recurrent state, and then the other thing is to show that you can't have two recurrent states that are equivalent to each other. And that's another proof that uses toppling in a beautiful way. So let me mention it. So suppose x is equivalent to x prime, and both are recurrent states. Okay. Well, then what that means that x plus m1 a1 plus mn an is equal to x prime plus a prime, m1 prime a1 mn prime an for some non-negative m's. This is the question that you raised, because I can put the negative ones on one side and then put the opposite on the other side, okay, and say this is equal to y, for example. Now, y plus kt. This t is the special number that I talked about before. Y plus kt for large k is going to topple down to x plus kt in m1 plus m2 plus mn steps. Because this vertex has so many things on it that we're going to be able to keep on removing A1 as many times as we want to. We're never going to get to a negative because K is so large that we've made all the components huge. So M1, I first topple at vertex 1 M1 times, and I topple at vertex 2 M2 times, and so on. I finally get down to X plus KT from Y plus KT. And on the other hand, it also topples to x prime plus kt in m1 prime plus mn prime step. And so now, therefore, sigma of x plus kt equals sigma of x prime plus kt. And this was equal to x, and this was equal to x prime by assumption. So, okay, I proved this, and if it was too fast for you, you can always look it up. So that's now this shows then by this long thing that the number of recurrent states exactly corresponds to the number of trees. Yep.
Oriented tree correspondence.
Exactly. Isn't that the question that you would like to have answered? And so, in fact, some people did find such a thing, and I believe the first people was somebody named Marino Lopez, proved in the Annals of Combinatorics in 1997. That there was a no, I'm sorry. It wasn't a one-to-one correspondence. The explicit one-to-one correspondence was found by somebody, but it was very complicated, and it wasn't, and it didn't have the other properties that people wanted. So, however, last year this paper was published. Brian, can you get? Yeah, you found it here. Good for you. The Sandpile model and Tut polynomials. It's in Advances in Applied Mathematics by Robert Corey. He's the one who wrote the first paper about showing tying it in nicely with graphs. And one of his colleagues in Bordeaux, and it's curious that he happened to be looking at the internet at my home page a day after I announced this lecture. He said, "Don, did you know that I have this nice one-to-one correspondence about sand piles?" And I said, "Well, how on earth did you did you ever find?" I just put a couple of sentences on my website, and he said, "Well, just serendipity." So I learned about this paper, and And in fact, I've got another way to present his correspondence, which I think is great, and I want to show it to you because I think it's really interesting. So that's the question: is that we would like to say, here's a recurrent state. What spanning tree does it correspond to? And for every spanning tree, let's give me a recurrent state. Give me the recurrent state so that I could do it. The reason is that, as I said, in mathematics, we like to have correspondences between things in one domain and things in another domain. Now, already in Corey's original paper, he showed this for some special cases. For example, the complete graph. He showed that the number of spanning trees in the complete graph is known to be, according to this notation, it's n minus 1 to the n plus 1 if there are n plus 1 vertices. He found that it was easy to get a correspondence between every recurrent state in the complete graph and what we call parking sequences, which arise in the theory of hashing. And it was known that the number of parking sequences was equal to the number of spanning trees. And then there's another correspondence that takes parking sequences into spanning trees. Well, he also took cases like wheels. If people studied concrete mathematics, we have a section there talk about the spanning trees of fans, and the Fibonacci numbers come up in there, and the number of spanning trees related to Fibonacci numbers. And he had a Fibonacci-like construction that corresponded to that showed how you also got the recurrent thing. But it was a complicated thing. Now we've got this beautiful new, fairly new construction, and I want to present that in the next few minutes. Okay, we haven't got too much time, but so I was going to ask for the audience to suggest a spanning tree, but now I'm going to give you a canned spanning tree in advance. So let's take our 3x3 torus, and I want to take an example of a spanning tree on it, but I don't want it to be an obvious spanning tree. I want it to show to show some of what goes on. So I'm going to say that remember that this wraps around. So I'm going to have an arc going from this guy up to here. So that's one connection from vertex 0, and also one coming down to 3. Now from this guy, I'm going to go over here and come in this way, and that's going to get over to vertex 8 over here. I'll put the numbers on here again: 0, 1, 2, 3, 4, 5, 6, 7, 8. Going to have the numbers. This pen is getting very dull, but I can continue. And then from 8, let's go up to 5, and 5 can get over to 4 and to 7 and down to 1, and 5 maybe up to 2. So this is one spanning tree on the graph. It has 8 arcs, and we can get from 0 to anywhere. And but if we want to draw it like this, imagine that the torus is a tile, and we repeat it, then we're actually getting the spanning tree looks like this, except that we're getting different pieces of it on the same tile. Are you with me? But anyway, that's a spanning tree, and I wanted to take one that was not too obvious, so we can see that we have a torus. Now the question is, find a recurrent state that corresponds to the spanning tree, and here's the algorithm. Watch. I'm going to just play through the algorithm, and this should give the intuition. So I list all the arcs of the graph first. 0, 1, 0, 2, 0, 3, 0, 6. Then there's 1 goes to 0, 1, 2, 1, 4, 1, 7, 2. I'm going to have to list these all, unfortunately. 2, 0, 2, 1, 2, 5, 2, 8. 3 goes to 0. 3 goes to 4. 3 goes to 5. 3 goes to 6. 4 has 4 things, 5 6, 7, 8. Okay, try to go fast, but I want, okay, 4 goes to 3, 1, 3, 5, and 7. 5 goes to 2, 3, 4, and 8. 6 goes to 3, 0, 3, 7, and 8. 7 goes to 1, 4, 6, and 8. And finally, 8 goes to 2, 5, and 6, and 7. Okay, I list them all. In general, we have a directed graph. The theorem isn't going to work exactly as it does for undirected graphs, but we still want to list all the arcs in some order. Now, so that's. Now I start out and I ask about the spanning tree. So I'm going to have a big branching process going here, and I'm first going to ask a question: I have a working set of vertices that I've sort of done with, and initially the working set is just 0. So I look at an arc from one of the vertices that I've already covered to another one, and I take the smallest such arc. So these are all these arcs are listed in lexicographic order here. So let's take the smallest. In fact, well, like these could be weights, and then we would. It turns out it relates to the minimum spanning tree if we took the arcs in order of weight. But I'm going to use lexicographic order here. So for this order, I asked the question: is 0, 1 in the spanning tree? And the answer is no. Okay. Now in my diagram here, I'm going to go to the right if the answer is no, and to the left if the answer is yes. And if it's not, that means then that I'm not dealing with this arc. Okay. Now, next question then, what's the next one? 0, 2. Is 0, 2 in the spanning tree? That's not in there either. So again, the answer is no. But 0, 3, is 0, 3 in the spanning tree? And the answer is yes. So now, what I'm going to do is I'm going to set x, well, I'm not going to write the y's and n's anymore. I'm going to set x3 to 3. And this is going to be my recurrent state. I'm going to be building it up here, and I'm going to put a 3 in this position. Now, why did I put a 3 there? Well, because 3 is now a known vertex. Originally, only 0 was known, and there are still. Okay, 0, 3. By the way, I have to cross out 0, 3. There are still 3 things coming out of it. And that's where I get the number 3. So when I add a new vertex to my set, I'm going to see how many things haven't been crossed off in its coming out of it, and that's going to be the value that I assign here. So you watch me play through the algorithm, and pretty soon you'll see what's going on. So my next question is: take of all I have known vertices 0 and 3, and the things coming out of them, the arcs coming out, the smallest one is 0, 6. Yep. 2, 0, exactly, very good, and 3, 0. Yeah, okay, I got to cross off. Every time I cross off one guy, I have to cross off. Right, so 0, 6. Is 0, 6 part of my tree? The answer is yes. Okay, so 0, 6 is part of the tree, so that means I'm going to set x6. Forget there's going to be a question mark here, but I don't have time to write the question mark. So I'm going to set x6 to the number of things left is that, so x6 also gets set to 3 here. Okay, now from 0, 3, and 6 leading to other vertices, what have I got? 3, 4 is the next guy to ask about. So 3, 4, is 3, 4 in the tree? No. 3, 4 is not there. So cross it off. 4, 3 goes away. What's next? 3, 5. 3, 5 isn't there either, so it goes out. Next is 3, 6. 3, 6, okay.
That's to a vertex we already.
What?
It's a new phenomenon. It's to it.
It's a new phenomenon. 3, 6 is not to a new vertex. That's true. And neither is 6, 3. So really, I'm asking for 6, 7 here.
You just cross.
What? Yeah. This isn't to a new. This doesn't go to a new guy. That's a good point. So 6, 7 is the one that I asked about. And again, 6, 7 is not there. What's next? 6, 8. And 6, 8 is there. So I set X8. Okay. So 6, 7 I had to cross out. 6, 7, 6 I had to cross out 3, 5, and 5, 3. Yeah. Okay. Hope I'm doing this right. X8 is now being set to 3. Lots of 3s. Okay. 8, 2 is the next thing, and the answer is no. So 8, 2, and 2, 8 aren't there. Because 6, 8 wasn't leading to a new vertex, you see. So 6, 8. Well, 8, 5 is the next question to ask. And X8, 5 gets a positive answer, and I'm at the bottom of my sheet here, but X5 is going to be set now to 2. So I'll put a 2 in here. And it will continue in this way, and yep.
The things that you're writing down on the left-hand column, you're processing them in a queue order?
This here?
Yeah.
These are my known vertices.
Right.
Then I'm looking, so I've got sort of known vertices, and then these are leaking out to unknown vertices. All the arcs that go from known to unknown, I'm choosing always the smallest.
Okay, so if you...
I've done it by hand, but I think I'm choosing the smallest.
Okay,
so I have somebody told me an ordering of the arcs, and in fact, any ordering is going to work. I chose here alphabetic ordering, but any ordering would work. But I have some ordering, which makes this a deterministic process.
You just mean earlier in the order.
What?
You just mean earlier in the order when you say smallest.
I mean that of all the arcs that are coming here, there's the one that's earliest in the ordering. Yes. Yeah. Or if the arcs were all weighted in some way, it would be the one that of least weight or greatest weight, whichever way you want to.
So if you're, at this point, when you add some vertex to that list, if there are edges that are coming out of that vertex that are lower in the order, you immediately start considering those.
Yes, indeed.
Okay.
That happens actually after 5 here. I start checking 5, 2, and then I check 2, 1, as it turns out. So I won't continue with 5 after I bring 5 into. I'm going to ask for 2, 1 before I look for all the 5s.
So every ordering of the vertices gives a correspondence between spanning trees and recurrent states.
Say that again?
Every possible ordering that you could have on the edges,
yes,
gives a...
Will give me a one-to-one correspondence between the recurrent states, yeah. And so I'm not getting only one one-to-one correspondence. I'm getting one for every ordering of the edges, which means, for example, for every weighting of the edges, like in a minimum spanning tree algorithm, we always choose the first edge that comes out. So if I had the minimum spanning tree, and if my edges were ordered by weight, then I would always take the yes branch.
And if the graph is a directed graph, but it happens to have an edge from x to y and y to x, they could have...
The directed graph, let me bring up later, because the directed graph is complicated.
Okay.
So I haven't kind of played out the whole the whole thing. If you do it yourself, you would find out that that you fill in x5 equals 2, and then you fill in x2 equals 1, and then x4 is 2, and then x7 is 2, and finally x1 is set to 0. And this turns out to be a recurrent state that corresponds to the spanning tree that I gave. Now, another theorem, which I will state but I won't prove. In a graph, in a balanced directed graph, in particular, this means that in degree and out degree are the same at every vertex. So in particular, for an undirected graph, it's always balanced. Then x is recurrent if and only if x equals sigma of x plus a, where a is equal to the neighbors of V0. In the matrix that I wrote down here, a is the negative of this of this top row here. So in my case, it's the neighbors of V0. This is a. So not only is it for x sigma of x plus t, where t was this fairly large thing with lots of positive components, it also holds for x plus a. And well, the reason is basically that a is equal to a1 plus a2 plus an, because the form of this matrix, you add up all the rows and you get 0. And so the sum of these guys is the negative of the top row, and so you're sort of adding 0 to that. And now the proof in the literature was faulty of this theorem, and so I emailed to Corey on Saturday, and he confirmed, and showed him my 5-line proof that's in the handout here. I mean, in the book, and he agreed that there was a bug in his paper, and that he can't think of any shorter proof right now of this theorem, but it's true. So, now, if I have a recurrent sequence, then take, for example, okay, if I have a recurrent state. Now I want to find the corresponding spanning tree, and what I do is I ask, first I ask if x1 is equal to 3, is my first question. And the answer will be yes or no. And the point is, this is going to correspond exactly to my previous to my previous method, because my first question in this one is 0, 1 an edge of the spanning tree? And the answer was no. So that meant that the next time around I would ask for something coming into 1. 1 was not going to have 3 guys left. So if x1, if I took the left branch, I was going to set x1 equal to 3. But if I took the right branch, somewhere along the line, x1 is going to be set, and the next time x1 has a chance to be set, it's going to be 2, and the next time it's going to be 1, and the next time it's going to be 0. So I'm going to branch and say, is x1 equal to 3? And the answer is no. Then I'm going to ask, is x2 equal to 3? And again, the answer is no. And x3 equal 3? And here the answer is yes. Yeah. And so at this point, I'll say, oh, 0, 3 was in the spanning tree. And if I add this vector a to, so add the vector 0, add the vector a to it, and you get 1, 2, 4, 2, 2, 4, 2, 3. And well, I'll topple this 4, and so this will now topple, and we'll get 1, 2, 3, 3, 5, 2, 3. and 0 here. And my next question is going to be x6. Is x6 equals 3? And the answer is yes, so I put 0, 6 in the thing. And I'll topple at vertex 6. 2, 3, 4. And what's going to happen is that the algorithm asking about the values of these recurrent things is going to exactly parallel the algorithm that built before, so I'll be able to reconstruct the tree that I had. And you have to play with this by yourself, but it's very beautiful the way it all fits together. So this gives a very nice intuitive correspondence. You know, we can psych out the way it's working. We can see that it looks like a lot of graph algorithms that we play with on spanning trees all the time, because a lot of spanning tree algorithms, you know, you start from known vertices and then you look at the arcs to the other ones. And as I'm going through here, I can figure out what are the known vertices, and I can then and if the next arc that I'm going to ask about in this part was 6 to 7, in this case I'll say is x7 equals, and then I just take the next lower number that I haven't ruled out before in previous branches, and that will be the converse algorithm and get me back the spanning tree that corresponded to the recurrent state. So that's the correspondence that happens. Now, what about so consequences of it? I brought some pictures here, and one of the crazy things you see is that sand piles, you can add two sand piles together. So if x is a recurrent configuration, if x and y are recurrent configurations, then x plus y, we can say, is equal to sigma of x plus y. This is an associative commutative operation. So we have an abelian group. We can add sand piles together. There's got to be a 0 sand pile. There's going to be, sand piles are going to have certain additive order. We know the structure of abelian groups, but in particular, there's a unique recurrent state Z which corresponds to 0 under addition. All right. So it turned out that well, okay. So under the theory of recurrent states allows us to define this operation of addition on the states, and therefore we now have an addition on spanning trees, the sum of two spanning trees. And some spanning tree is, there's a spanning tree that somehow represents 0 under a particular ordering of the thing. Now this to me is mind-boggling. I have no idea how to intuit this, what's it going to mean. And there are zillions of interesting graphs in the world. You think of planar graphs, think of grid graphs, torus graphs, complete graphs, cycles, all kind of product of graphs, series parallel graphs. Your favorite class of graphs, each one has a way to understand its spanning trees as sand piles, and then to add spanning trees together. And who knows if this is going to lead to some great applications until we play with it and find out, and get more experience with these things. Okay, in a finite abelian group, you always have a unique element of 0. So
without a 0?
This is, you see, you have inverses as well. I mean, it's not just commutative mono. You have, if x plus y equals x plus z, then y equals z. Yeah, that's the cancellation law. But you also have a 0. In fact, that I guess T is, Z, anyway, one way to get it is Z, you can take it as, for example, 2D minus sigma of 2D, and then reduce that. 2D has large components, and then we subtract off sigma of 2D, and then this is equivalent to 0. And then the reduction of that is a recurrent state. So anyway, that's one way to compute Z for sure. By the way, I found in every case I tried, Z was a multiple of A. But I haven't proved that's true.
Are there any orderings in which the Z you get is somehow intuitive?
Well, first of all, the Z is unique. Z occurs, Z is a sand pile. It doesn't depend on an ordering. So I tried the different toruses here. In fact, the first one I tried was the 3x3 torus, which we have here, and it has only 3s and 2s in it. The white means just take the center of this picture, because I'm repeating. Imagine I'm repeating it over and over on a plane of 3x3 tiles. And then the next one I tried was 7x7, and I had this one. And I started to think, oh man, this starts to look like the recent election. Again, I had only 3s and 2s. But then this was the 6x6, the 5x5. So here blue is 3, and red is 2, and yellow is 1. No, wait, and green is 1 and yellow is 0. So here are some green ones coming in the 8x8. The 9x9 had no yellows. This was a 10x10.
Is this not dependent on the choice of ordering?
So this doesn't depend on, this is the 0 sand pile for a small torus.
Okay.
It's uniquely defined as the one that's in the equivalence class containing 0. This is the recurrent state. And so I wasn't able to psych out anything, any pattern. I mean, it's easy to see that the neighbors of V0 have to all be blue, but other than that, I didn't. I was hoping, of course, that this would be a pattern that I could extrapolate to infinity. Then I tried squares instead of wraparound. I said small squares. What are the 0 sand piles there?
Yeah.
And they, so it doesn't. Unfortunately, it just, I put the hole in the middle too. Here I have like a 15 by 15 square grid, and V0 is the middle vertex there, and it just it has eightfold symmetry, but it doesn't give you any pattern it's just like looking through a kaleidoscope. It looks kind of nice because it's got symmetry, but I didn't see anything else to commend it. So maybe so in other words, there's lots of open questions here. The answers to some of them might have terrific applications. Some of them, might just be interesting. Some of them might just be weird. And there's just no good mathematics. But we know that, for example, in the complete graph case, the 0 sand pile is everything has the maximum, like all blue, corresponding if it's complete thing with n plus 1 vertices, the complete graph. The 0 state is easy to see. It's just put n minus 1 on n minus 1 on everything. And similarly for probably there's something that you can do with series parallel graphs and things like that. But I don't see any pattern for these toruses and grid graphs at the moment. Okay, well, it's getting to be 6 o'clock, so I covered pretty much what I wanted to say, except for a couple of really surprising things. Okay, I said, first of all, that there's this mind-boggling connection between, that is even now not only now we have a connection between trees and sand pile, and so that means we can add trees together. Now this connection depends on the ordering of the arcs, but still that's not such a weird idea, because when we study minimum spanning trees, when we study matroid theory, we usually order the the edges of the matroid or the elements of the matroid. We usually order things when we have a lot of algorithms with trees. So and a correspondence depending on order is no big deal. And in fact, the minimum spanning tree is exactly the one that has every vertex has dj minus 1 grains of sand on vertex j, the degree minus 1. Because that's the yes branch all the way through. That's where we find the minimum spanning tree. What's the zero spanning tree? That I haven't got any handle on at all. Furthermore, this one-to-one correspondence, I described it only worked for graphs, not for directed graphs. With the directed graphs, it's very interesting, and as far as I know, it works only for the balanced directed graphs. A balanced directed graph means Eulerian graph. It means that every vertex has as many things coming out of it as coming in. But they can go in strange ways. But you have to have as many going out as coming in. Now, but the funny thing is you try to generalize Corey's one-to-one correspondence for directed graphs. And it works a very funny way. It gives you a one-to-one correspondence between recurrent states, recurrent states and out trees from V0. Now, I told you what an oriented spanning tree was. It says that every vertex has one, except V0, has a branch coming out that goes toward V0, and that means that's an in tree into V0. But an out tree is one where every vertex other than V0 has something coming from V0, and so that means that V0 to that one. Now, in a balanced digraph, if you have a source, it has also a sink, and but this method that I gave you here, this branching method, actually it doesn't give you a connection between recurrent states and in trees, but with out trees. However, and it's something I never realized before I studied this problem, the number of out trees in a directed graph, in a balanced graph, is the same as the number of in trees. It's because the determinant of a transpose of a matrix is the same. So when you have a balanced graph, imagine that you have an arbitrary matrix here, but I put on the diagonal I put the out degree of every vertex, and then but now it's not a symmetrical matrix anymore because everybody has as many things coming in as going out. So the sum of the rows is still 0. But the matrix isn't symmetrical anymore. But the number of out trees is the determinant of the transpose of this matrix, because the diagonal stays the same in the other things. So I never realized before, but nobody has ever, as far as I know, found a one-to-one correspondence between out trees and in trees in a balanced directed graph. Maybe there's one out there in the literature, and that would be, very interesting to me. And tomorrow I'm leaving for Europe, and I'm going to spend 3 months, and I'm going to be in Sweden with some of the best commutatorists in the world, and I'm going to see if any of them can figure out, how to do more with these ideas. And one of the things that I think is not obvious is to find a good way to a one-to-one correspondence between all out trees from a vertex and all in trees. But this one-to-one correspondence is funny because it gives you the out tree. Now I think that was the main thing I wanted to mention. And the other part is then that if you don't have a balanced digraph, the theorem is still true that the number of recurrent states is the number of oriented spanning trees. But there, I have no idea what kind of a one-to-one correspondence could exist, and I tried the simple graph with 3 vertices, but any number of arcs going between them. You can have multiple arcs. It doesn't matter. In this definition, everything works fine if you have two arcs going between vertices. And then you just pass 2 grains of sand each time you topple. So in the 3-vertex case, you can, the theorem is still true that the number of recurrent states is the number of spanning trees, but I looked at you try to find a correspondence, and it just baffled me, even though I'm working on a very small, simple problem with only a few parameters. So there. Oh yeah, one more nice idea, and that is if you look at all the recurrent states, they also form what's called an order ideal. It means that they're closed under. If one state is greater than or equal to another, if I have a recurrent state and I have another one that's bigger than it, this bigger one is obviously also recurrent because I could add another grain of sand to this. So the set of recurrent states is totally determined by the minimal recurrent states, the ones that you can't take away any of their grains of sand without being non-recurrent. So I computed all the minimal. Oh yeah, here we can zoom in on this. These are the stable states that are equivalent to 0. There's 16 of them, it turned out, in this particular example. Some of them were a little surprising, but they're all equivalent to 0. But only this one is recurrent. But now, if a minimal recurrent state, like 0, 1, 0, 2, 3, 3, 2, 3, is a minimal recurrent state. That means that 0, 0 is not. You subtract 1 from any of these guys, and it's no longer recurrent. And this one is also recurrent. You change the 2, 3 to a 3, 2. Any 2 minimal recurrent states are non-comparable with each other. The total number of minimal recurrent states was 1,336. I don't know any good explanation for that number. It was 2 to the 8th, 2 cubed times 167 or something like that. But in the case of the complete graph, the number of minimal recurrent states turns out to be just n factorial. So there's something about minimal recurrent states that also deserves to be investigated. So figure out how to enumerate the number of minimal recurrent states for these sand piles. That's another open problem. And I think open problems galore if we keep playing around with, take a graph, start playing a sand pile game. It raises questions, then you can get some answer for it. You find out, what's the sand pile group? How many, is it a cyclic group? Is it the fact, it's got prime numbers in it somehow, as far as the orders are concerned. Lots of questions seem to be natural for every graph, just like people started applying topology to graphs years ago, and so that led to lots of wonderful theory. So I imagine there's a lot of stuff is ready to bust open as people start studying this connection with sand piles and graphs. Yeah.
Says that all of the non-recurrent state we have, then we can go down to some specific recurrent state, right?
Yes.
Then
a non-recurrent state will eventually lead to a recurrent state. Yes.
Right. Then we can group a non-recurrent state depending on what recurrent state they are going to.
This is right. And this was the equivalence relation that I defined.
I mean, is there any rules or some mathematical meaning or direct meaning that that's such group of non-recurrent states?
So I haven't got a good idea for how to find out exactly how to compute all of the elements equivalent to a given one. What I did was, in my program, I took every state and I took all 65,000 states and I used the union find algorithm, taking everything saying x is equivalent to x plus a. and then that reduced me to the right number of equivalence classes. But I haven't got a good algorithm for solving. There are some good. I'm trying to remember what's the complexity. Maybe Dan would know. Given an integer matrix, what is the or integer lattice to tell whether two vectors are equivalent to each other. With these, wait a minute. I guess this is fairly easy because I can triangularize use Smith normal form on the matrix, and I could test whether two things are equivalent. But to test whether they're recurrent is this other test where you add x plus a and then see if it reduces. I haven't got a good characterization other than this trickle down reduction. Now there's one other thing I forgot to mention, though, is that when you take a recurrent state x and you add this vector a to it, this magic vector a, which is just the neighbors of vertex 0, then what happens always is that you do exactly n topplings. Every vertex topples exactly once, and you get back to x. And the reason is, you see that a is equal, I wrote it down, a is equal to a1 plus a2 plus an. And so x plus a is reducing down to x. And each one of these is toppling. And these vectors are linearly independent. So there's no other way to do, so you always have to topple each one exactly once in order to get down to, in order to get from x plus a down to x. And so this is an n-step process, an n-step test for recurrent state. As I said, I conjecture that the zero vector is always a multiple of a, but I didn't. Maybe it's obvious. I just haven't seen it yet. It was true in every case I tried. I looked at zero vectors also on the 3 by n toruses where 3 was fixed and n was growing, and I didn't see a pattern.
Study these sand piles. What kind of questions are they interested in?
When the physics people study these sand piles, what kind of questions are they interested in? I think they're trying to find questions like the entropy. They're trying to find out some kind of spin numbers about these things or something like this. They have certain statistics that they calculate on the states. See, Dar observed that in the limit, if we keep adding sand at random, each of these recurrent states is equally likely. I don't think he showed how fast it converges to the limit, though. So this wouldn't give us necessarily a good way to generate a random spanning tree. But that you can anyway. There's pointers to the literature in these papers, and it's easy to search on Google for the different things and look up sand pile. Sometimes one word, sometimes two. But they'll more be concerned about computing some kind of energy or something, temperature, things like that, which is combinatorics. People are more interested in seeing one-to-one correspondences and smaller examples. I don't see how I get anything continuous out of this right now. Lots of great questions. You people are. I need a referee to choose who's going to get these prizes. Yeah.
Is there any application of this to analysis of petrinets? Is there any application of this to analysis of petrinets?
Analysis of petrinets. Well, I bet you there is. Yeah. Certainly, it's very much like firing on petrinet. Yeah. So I mean, sometimes some people have studied like an infinite number of states, and you keep on going until there's no V0, but things sort of go out to infinity, and then then you only consider small configurations instead of the recurrent states. But Petri net looks very much like this kind of theory, doesn't it? You know. Or Petri nets for the Germans in the audience. Well, thank you very much. And now I don't know how to decide who's going to win the prize, but I think I will. Those of you who think that you deserve it, come up, and then I'll choose between you. So, Merry Christmas to all.